Okay, let's get started. So, my original plan was to start today talking about the autoencoders that I mentioned previously, but then I realized that I'd forgotten another point which I have to explain to you first. One is to understand the whole concept of what we are doing there, and is related with it is also that for our autoencoder we need an appropriate loss function. That loss function will be the Gamma-Poisson distribution, also known as the negative binomial distribution. And who already knows about this distribution? Anybody ever heard of the negative binomial distribution? Thought so. Okay. So let's, and hence I first go through that thing, and then we later get through the theory of how we use this for the autoencoder or for denoising. But the original way where this whole negative binomial made its way into biology was because of the question of how you actually see whether a gene is differentially expressed, and that question came up first in the context of bulk RNA-seq. So you know this whole single-cell RNA-seq is rather new. That occurred only in the last 5 or so years. But what's much older, maybe 20 years old, if not a bit more, is bulk RNA sequencing. So at the beginning, RNA sequencing was always understood to meaning that you have a whole bunch, a big tissue sample comprising billions of cells, and you just extract all the RNA from these cells. And hence you get, then you compare samples of different kinds between, for example, disease and healthy and the like. And now you want to look for genes which differ strongly. And obviously, you want to know whether the difference between between your different sample groups is statistically significant. And to give you some idea of what this all has in mind, let me quickly look for a little example. And this is from a completely unrelated work, but it has this little app in it that we once made long ago, which might be helpful to understand as an example. So here, as I said, this is a web page which described a rather unrelated thing, an R package that we've written a while ago in order to make interactive visualizations. But in order to demonstrate it, we used a bulk RNA-seq data set, which we've chosen because it's pretty prototypical standard. It comes from this publication here, Conway et al. Elucidating drivers of oral epithelial dysplasia formation and malignant transformation to cancer using RNA-seq. It's 9 years old. It appeared in OncoTarget, which I guess is sort of mid-ranking biology journal. It didn't make too much of a stir emerge in this paper. But it's a typical example of this run-of-the-mill standard application how RNA-seq was used in clinical research over the last 20 years. So what these people did is they collected tissue samples from people with mouth cancer, or oral squamous cell carcinoma, OSCC, so a cancer on the inside of your mouth. And in that cancer, it seems that the tissue first becomes strangely shaped, like you get some growth out of the inside of your mouth, and then finally, at first the growth seems to be non-malignant, like it's there, it's ugly, it's annoying, but it doesn't grow out of control, and then it becomes malignant, by which medical people mean it grows in uncontrollable fashion, like exponentially, and hence is a tumor which potentially can kill you. And so from each patient, they had 19 patients. From each patient, they took 3 biopsies. One of healthy mucous membrane of the inside of the mouth. One from this dysplasic tissue, which already looks like malformed, but isn't malignant yet, and one from tumor tissue, so actually tissue of uncontrolled growth. And they wanted to see which genes actually differ in order to understand how the gene expression pattern differs from how the gene expression pattern differs when with ordinary epithelial tissues or the skin, the inside of your mouth turns into tumor. And we did this for 19 patients because obviously every person is different. So if you see something in one patient, it's not at all clear whether this is now a standard feature of this tumor or just an idiosyncrasy of this one patient. So it's important to know whether this really holds for many patients. And to do that, and now I show you here this app that we did. So what they did is it's bulk RNA sequencing, which means they started off with a tissues with a count matrix like this. As you can see here, for each gene, each row is a gene as usual, and each column is now not a cell, but a whole sample. For example, here the normal, the dysplasic in the tumor tissue of patient 4, and then normal dysplasic in tumor tissue of patient 38, and this way it goes on all to the end. And for each of the genes we have numbers. You notice the numbers are much higher than they used to be. That's for two reasons. First, this is bulk sequencing data. We are not limited by looking at a single cell. Each sample comprises billions of cells, if not trillions. And we sum all of them up, so we have plenty of RNA. And hence it's quite typically that you get from each sample something like several million reads, and then a few hundred, a few thousand, or even 10,000 reads for each gene. In this specific thing, we went a little bit overboard with the thing and actually paid for a whole sequencing lane for each individual sample. So we didn't get the user 3 million, but they got 30 million reads per sample, which didn't help them anything of getting better results, only gave them a big bill, so that was a big waste of money. But of course for us it's useful because we can now see a really strong data set. Here you see this typical comparison of the count matrix with dysplasic tissue on the y-axis, the normal tissue on the x-axis here for one specific tumor, number 4. Each point is a gene, and as you can see for most of the genes you have a good agreement, and for some genes which stick really out. Now obviously, as we've discussed often, even if you were to take aliquots, so portions of the same prepared sample and split it over 2 lanes and sequence the same sample twice, you will not get the same numbers simply due to Poisson noise. Hence you can imagine that the bulk of the width of this distribution here is due to Poisson noise. Because with the logarithmic scale, it tapers down and becomes more and more narrow because of course Poisson noise, when considered relative to the amount, so the coefficient of variance of Poisson noise drops with the square root of the mean, and hence these things have much less. The strongly expressed genes seem to agree quite well. But even those have difference, which is obviously simply for the fact that it isn't twice the same sample, but it's 2 different samples. And we might now ask, is this difference here more consistent? Is this gene always a bit higher in dysplasic than normal tissue or not? And to do this, what we can do is we can now split to one comparison. Either we say we compare tumor to normal or dysplasic to normal. So for what I do now, I will compare tumor to normal. And for this tumor to normal comparison, I just look at each of the 19 patients and always ask what is the expression ratio for a given gene between tumor and normal, and is this expression ratio consistent between all of them. I might simply do a t-test to see whether these expression ratios, whether the average of these 19 log expression ratios, whether this average differs from 0 or not. But we will come in a moment for a statistically more appropriate test with a single t-test, and that's the gamma-Poisson GLM. But first, how does this look like? So here we have done such a test. It was actually a slightly different test, and this is what they call an MA plot, where the x-axis is the average, each point is a gene. The x-axis is the average expression strength of this gene, averaged over all these 3/19 samples, and the y-axis is the log expression ratio on a log 2 scale. So this is a gene very highly which is consistently high, and what I've now done is in this app here I can click on one of these genes, and then I see the individual values to the right, and can see that yes, indeed in all the patients the tumor is much higher than the dysplasic thing, with the notable exception of this one sample. So this is a typical example for a highly significant gene, highly significant in the sense where the tumor sample is much above the normal sample in regards of expression of this gene for 18 of the 19 patients. So we can say that probably this cell coming up is somehow causally related to the tumor, because we don't know whether it's an effect of the tumor or whether it might be one of the causes. Dysplasia was with, so from each patient they took 3 samples, one of healthy tissue of the mouth cavity, one of already malformed tissue, that's dysplasic, and one from fully grown tumor. So it's an intermediate state between healthy and tumor. And I thought that was a bit of a question that I wanted to ask here. That's why I made it, and you can click a bit through them to see which of them are intermediate or not. Obviously, clicking through lots of them is not that productive. The more useful thing would be to calculate the average log ratio between tumor and normal on one axis and the average log ratio between dysplasic and normal between the other thing. And then if it's in the middle, I should expect this to be sort of one octet of the other thing within the first octet of the scatter plot. Yep. But the point why I like to show this app when talking about RNA-seq expression, because it typically shows you the typical how much the typical extent of biological variation when you compare different individuals, like different patients, and you can see how much there's how the fold change, the extent of the fold change is pretty can differ quite a lot in some patients. There's a really strong change between normal and tumor, and in others it's only a little bit. And what in the end we want to do is we want to get an idea about the sampling distribution, so what distribution does this log ratio seems to be drawn from. We assume that it's drawn from the log normal distribution, or the log ratio from a normal distribution. Of course, we want to ask, is this distribution far enough moved away from the 0 that we can say, yes, we can say for sure that the gene goes up or that the gene goes down. And all these black ones here are genes where this is not so clear, where it goes up in some, or where it goes down in the other, and overall the variation between patients is too much as to allow us to put confidence in our claim that we know what the sign is. There's a little subtlety here. Usually when statisticians explain statistical significance and talk about something like a t-test, what they like to do is say that sorry, today I guess I should have taken another coffee. My brain can't quite keep up with me talking. So in classical statistical hypothesis testing, you have some hypothesis which could be completely wrong. Like you have a hypothesis that blue-eyed people consume more potatoes than green-eyed people. If you have these kinds of typical classical hypotheses, your null hypothesis, there's no connection between the two things whatsoever, is a reasonable null hypothesis. And the whole point of Fisherian hypothesis testing is to ask how much evidence do we have to refute this null hypothesis and really have evidence that this effect that a priori we don't consider likely is actually there. In RNA-seq or in expression sequencing, this is not quite the case, because if we formulate the null hypothesis, there is no difference in expression between tumor and normal for this gene. We can refute this null hypothesis already from biological arguments. Namely, we know that all genes are interconnected. There's a huge regulatory network with lots of feedback loops, and whenever in a biological system you pull somewhere, everything else will change. Maybe over several hops, like this gene changes that gene, which changes that gene, which in turn changes something here in the cell, which changes this chemical reaction, which again changes this gene. So a priori, we can already say a priori that as soon as our outer condition, our predictor, in that case tumor or normal, has any effect whatsoever on gene expression, of course it has, we're talking about cancer, we can already for sure say that there's no gene which will not be affected. But sometimes the effect will go through so many hops that you can't even tell from the data whether the gene is overall upregulated or downregulated, simply because all the other influences on the gene caused by all the variation between the subjects, so simply caused by the fact that these are different subjects, these variations are much stronger than the effect of the tumor, so the effect of the tumor will drown in that, and we can't see the effect of the tumor. Hence, whenever looking at RNA sequencing, the proper formulation, at least in my opinion, is that we are not, our p-value and our statistical significance doesn't say us whether there's an effect, but it says us whether we have quantitated the effect with sufficient precision to get the sign right, to know whether it goes up or down. Because, of course, if I put a confidence interval around this estimated average log expression and the confidence interval overlaps with 0, then we can say that both signs are plausible, and hence we cannot say what the direction is. So that's what the red color here actually means. We have sufficient confidence in the sign. So, and what I want to talk a bit about today is how do we perform these statistical tests, and what's the correct statistical procedure. And we get to this, of course, in our RNA-seq data, in our single-cell RNA-seq data as well. You remember last time we looked at this data set of, what was it? Right. Where we had the peripheral blood, and it was stimulated with some interferon, so that the immune cells thought that they get attacked, and that activated the immune cell, and we wanted to know which genes are which genes react. And we wanted to do this specific for each cell type, and we already said last time a good way to do that might be to estimate for each gene to calculate the average expression within each cluster, maybe the cluster of the natural killer cells, or the cluster of the T cells, or the cluster of the B cells. For each cell type, I just add up all the sums. We call this a pseudobulk, because it's like the old-fashioned bulk RNA sequencing. Once we put all the counts from all the different cells together and add them up to one sum, it's like we did the bulk experiment. Of course, we now have the advantage that in a real bulk experiment, we can't quite, we have difficulty controlling which cell types are in our sample unless we can use FACS machine, flow cytometry assisted cell sorting, a technique to sort cells by cell type. But this is cumbersome. We can only sort by criteria we know a priori, and of course in single cell sequencing we can define our clusters post hoc, and can then also ask post hoc about on which level of granularity do I want to calculate this. The simplest thing what we can do here in this example is of course just adding up over all the cells, and hence pretending that we do we just do an old-fashioned bulk RNA-seq experiment where we just mash together all the blood cells. As I've just said, it's important that we are aware that any difference we might see here are idiosyncratic to this one patient from which we got the blood. And hence, in that paper that we used last time as example data, they actually didn't use only one subject, they used 8 subjects. And they mixed them all together, and then they teased them apart again by looking in the sequence of the RNA for polymorphism, so for differences between the subjects, and so that allowed them to do this by subject. And that's what I've done here. We have the subjects which have numbers, subject 101, 107, 1015, and from each subject we have the control and the stimulated sample, and I simply added up for each gene the counts over all the cells. And of course, I did this quickly, and the more useful thing would be to not add up all the cells, but to make such a count table separately for all the T cells, for all the B cells, for all the NK cells, or maybe even do a more fine-grained and do it for all the CD8 T cells and all the activated T cells and all the whatever. And we can now ask how to estimate, how to perform statistics on that. Now, a very helpful thing when you try to understand statistical procedures is to not start with real data, but instead start with simulated data. And that has One is, if you simulate the data, you know the ground truth. You can simulate both the situation that you have, that there is a real difference or that there is no real difference, and we can try out whether your statistical procedure is able to call this difference. The other part, which is often underlooked, but it's equally important, is when you simulate the data, you have to think about how you simulate it. You have to explicitly write down a generative model to do the data, and by this you have to specify how you assume the data to what mathematical, what parametric assumption about the underlying distributions you make. And that helps a lot in reading for it. And it's a bit something that I'm always a bit disappointed about statistics textbooks, because I feel often they omit talking about the underlying distribution first and only add this at the end, which often makes it hard to understand. So let's here use the simple example where we say we have a gene of which we assume that that 1 in 100,000 RNA molecules come from this gene and all the others from other genes in group A, and twice as many in group B. So I have sample groups, let's say 10 samples of group A. That might be all, I don't know, mice which with a certain condition, and group B might be mice without this condition, and you can take out some tissue, quantify a specific gene or whatever. So we want to compare these two groups, and from each group we have 10 independent replicates, 10 independent sampling units, which might be a new mouse or a cell sample or a tissue sample from a patient or whatsoever. And in this case it's not paired, so the samples from group A and the sample from group B are independent from each other. In our other examples it was always paired, because for each normal tissue sample we had a tumor sample from the same patient, and we'll see later how we distinguish that. But if you remember the t-test, you remember there's a paired and an unpaired t-test. It was the same. So I make an unpaired data here for it. And I say at the beginning it's 10 to the minus 5 and 2 times 10 to the minus. This is sort of the expression difference that I actually look at. The gene is has an expression twice as strong in group B than in group A. And I take the logarithm and say this is the true mean log fraction. So by log fraction I mean the logarithm of the fraction of all the reads which go onto that. So that I assume we have 10 samples. And furthermore, I want to now ask for each of these, 5 times sample A, 5 times sample B, and now I ask for each of these 10 samples, what is the actual fraction? The expectation is minus 11.5 for A and minus 10.8 for B, but our actual fraction might tether a bit around these values. And in order to do this, I take a normal distribution here around this true log mean fraction, so this value or that value, and I've chosen standard deviation of 0.5, which if you go back through the exponential is maybe a fold change of up or down, twofold, threefold. And because this was the log mean fraction, I want the actual true mean fractions I exponentiate. And as you can see, the individual ones are around 10 to the minus 5, and the second and the group B ones are around 2 times 10 to the minus 5. The next thing I need to simulate is this case of the total count. How many reads have I got in total to compare this with? And here I've just again used a log normal distribution for this, and this sample has a total of 1.8 million reads. So they have between 500 and 2 million reads typically. And now I ask, if this is the expected fraction, how many genes do I count to actually get for my gene? And this is where I use the Poisson distribution. So in R, the R plus function says, draw me 10 Poisson distributed variates, and for each of them take here the product of this with that as the expected number of reads that we get. And we get this as the expected number of reads, 10, 1, 49, 4. And now I want to see, is there really a difference between this and that? And the first thing I can do is to do a completely normal t-test. So I divide because this is up to here, it was simulated data. This was sort of unknown to the experimenter, and this is now the data that the experimenter would get. These totals and these individual counts. And if I divide the individual counts by the total, and as we always do, multiply by 10 to the 4, or this time I multiplied by 10 to the 6, because this is now simulated by data where the counts are much higher. So typical totals is not in the area of a few 10,000 or a few million, so I will take here 10 to the 6, add my pseudo count, and now I get here these log expressions. And as you can see by eye already, the group B, so the latter 5 are a bit higher than the group A, so earlier 5. And I can do a t-test comparing these two log expressions, and it gives me a p-value of 0.02. So it basically has inferred that that the data seems to fit best with this. Yeah, you remember how a t-test works. You look at the difference between the two means, estimate from the pool standard deviation a standard error, run the whole thing through the t-distribution, and then you get your p-value, which tells you the probability under the null hypothesis that the true mean is the same in the groups. The probability of seeing a difference of at least as much, like 0.9, is only 2%. Only 2%, because as we later say that this data will see, this probably wouldn't be good enough to call this differential expressed. And now what we will later use is this Gamma-Poisson GLM model, where I put the same data in it and call this function here, which I'll explain in a moment. And this time I get a much better p-value, 0.0005. And before I can explain to you what this Gamma-Poisson, what this GP-GLM does, I have to explain GP, the Gamma-Poisson distribution. So above, when I write down what we've done above, this here is our generative model. You see, we set the counts that we get for our gene of interest in sample I follows a Poisson distribution with some given total count and a given fraction. Q is a fraction of all the reads which fall onto this gene. And it's a Poisson distribution conditioned on this fraction. And the Q itself, we said, is log normal distribution. Okay. So it follows, its logarithm follows a normal distribution with a given mean, which is the same for all the samples from the same group, but it differs between the group A and the group B. So P of I is supposed to be A or B, one of the two groups. And the standard deviation of this log normal, we say, is always the same, which will, is typically in all ANOVA-like standard assumptions. So this was our generative model, and if we now want to fit specifically this model rather than doing a t-test, because what we've done here, the t-test feels very weird. We went through this logarithm and in a way did a lot of transformation on the data, which probably is not that well motivated. So what we now do is we look at this thing. We ask, can we do a maximum likely estimate to estimate our two distribution parameters, eta and sigma, from our data? And for this, we have to take this likelihood, consider it as function of the of these two parameters, and maximize it. But in order to maximize it, I have to marginalize out the nuisance parameter Q, because Q is not observable, I can't see it. So what I have to do is, I have to average over, I have to integrate out the Q by saying the probability, this probability mass function to observe K counts is given by this integral, which as you see is the Poisson distribution to get K counts if the Poisson has the right parameter Q, multiplied by the probability that Q has this right parameter if we draw it from this log normal. And if we take this and if we want to integrate out this thing, will turn out that there's no closed form solution for this integral if you put in the probability mass function for the Poisson and for the log normal. Before I just notice I've skipped over that part, which I should quickly explain. If you look at this generative model, what we can of course easily do is ask what are the first two moments, like what is the expectation of K and it's easy to see that the expectation of K, so of the counts, is the expectation of Q times S, because it goes in here. I say here expectation of Q because the expectation of Q is not eta because it's log normal. The log normal because it's skewed, the expectation is actually eta plus sigma squared half. That is why I don't write it out. And importance, the variance of this K is there's this law of total variance, which shows you how to get the variance of the conditional distribution. And you either have to take the expectation of the variance plus the variance of the expectation. And if you do this, then you notice this, the variance has these two parts. The left part comes from the Poisson, the second from the log normal. The Poisson, of course, has a variance equal to the mean, SEQ, and the log normal contributes an extra part. And we call this an over-dispersed Poisson. And this is something you have quite commonly. If you look at data, you notice that it's Poisson distributed. Whenever you have count data, your typical first assumption is that it is Poisson distributed, that it follows from a Poisson distribution, because virtually all count processes are typically either describable by a Poisson distribution or by a binomial distribution. But you will often find out that the data is, that the variance is larger than the Poisson predicts. In physics, we also sometimes get the variance smaller if we do squeezed stuff in quantum mechanics and have the sub-Poisson statistics and super-Poisson statistics. Whenever quantum mechanics is not involved and we actually just count something which is gathered by a random process, it's quite common that it's over-dispersed, as the statisticians say. That means the dispersion is larger than what the Poisson expects, and of course the over-dispersion is always a consequence of the rate parameter of the Poisson itself being drawn from the distribution, and we have to take the variance of this distribution to get it. So, this fact here, that the variance so neatly decomposes into the Poisson variance and the variance coming from the underlying distribution of the rate parameter, that will always be the case, no matter what distribution we assume for Q. Whether we assume the log normal distribution or replace this by another distribution. And we have good reason to replace it by something else, because I told you this integral cannot be solved, or can be solved but only numerically. And if you do maximum likelihood estimation, you don't want to recalculate an improper integral for numerically for every single operation. So statisticians, being practical people, have found not only being practical people, but also being people who have already been around before computers, where a numerical integration of wouldn't have been an option at all, quickly thought about how to solve this issue, and decided, let's simply replace the log normal by another distribution, which allows us to get a closed form solution of the integral. And this happens to be the gamma distribution. The gamma distribution is this distribution here, this, as you can see, which is named simply for the fact that the gamma function appears in this normalization process. And yeah, it turns up in all kinds of statistics. The most important way how it naturally occurs is from the chi-square distribution. So the chi-square distribution, this distribution of the sum of squared normally distributed values, and if you try to integrate, and the chi-square distribution has this degrees of freedom parameter, which tells you how many squared normal variates you have summed up, and hence this degree of freedom parameter is always integer, but you can interpolate between them and also ask what is the generalization to non-integer ones, and then you get this gamma distribution. But the more important thing is that the gamma distribution has a tighter relation to a Poisson distribution in what Bayesian statisticians call conjugate distribution, in the sense that if you multiply one with the other and integrate, we get back one of the two. And this is what we also use here by actually saying we replace the log normal now by a gamma distribution as follows. I again say So to make my life easier, you might have noticed I dropped the S by now and always say S equals 1 from now on. So I take my Poisson distribution, replace the log normal by gamma distribution, and the gamma distribution is usually parameterized by shape and scale, as you can see, but for today I want to parameterize it by its mean and variance. It's a two-parameter family, so you can always parameterize it by the first specifying the first two moments. So in here, this is the gamma distribution, and this is the Poisson distribution. In the Poisson distribution, Q is the mean. In the gamma distribution, if I want to consider this as a function of mean and variance, and of course I have to tell you that mean and variance are related to these two shape and scale parameter, via mean is kappa theta and sigma squared is kappa theta squared. And if you now put these two distributions into this integral, then the integral actually a finite distribution falls out, namely you get this thing here, which has this shape, a binomial coefficient that I've written here with three gamma functions, and this part here. And as you can see, this looks very much like the binomial distribution. In case you can't remember, this was how the binomial distribution looks like. N over xp to the xq to the n minus x, so a binomial coefficient plus times these two powers. And yes, it looks more or less the same, even though not quite, because here the exponents change strangely, and you get, but we get this, and this is what we now call the gamma Poisson distribution or the negative binomial distribution. People call it the negative binomial distribution because it looks like the binomial distribution, and if you try to write out this binomial coefficient here, you will find a minus at the strange thing. So the first person to come up with it that, oh, this looks like the negative, like the binomial, only with the minus, let's call it the negative binomial, which probably has confused all students since, because the thing it has nothing to do with is the binomial distribution. More recently, some people decided this is a stupid name, let's call it the gamma Poisson distribution, because that's where it comes from. This is why I now write GP, as people finally convinced me that maybe that's a better name. And so I write GP instead of NB. The gamma Poisson distribution also comes from the fact, usually, traditionally comes from a different thing, namely from a waiting time quests. You do Bernoulli trials, like throw a coin or so, where you have a certain success probability, and you know in the normal binomial you always ask the question like, if you do 20 trials, what's the probability of getting exactly 3 successes? And you could also ask a so-called waiting time question, where you ask, if you want to see at least k, if you want to see exactly k successes, what is the probability that you need that you will occur q failures until you have seen your k successes? And the answer to this question is also the negative binomial, and that's where you can also derive the same formula, but in that case, the number of successes you want to see is k, and the number of failures, the k is the number of failures, and r is the number of successes that you want to see, or the other way around. And you want to see r successes, what's the probability that you need k failures? So this is the original meaning of this k and r, and p is the success probability in this waiting thing, but you can also translate them in a mu and in an alpha, in these other parameters. And if you do that, then you actually find the gamma Poisson distribution comes out of the integral, taking over the mean of the gamma and the variance, and also the variance of the gamma. And the actual variance of the gamma Poisson is the mean of the Poisson, is the variance of the Poisson plus the variance of the gamma, and it's usually parameters like this with this alpha here, that you can say variance is mean plus alpha mean squared, because this means that alpha is something like the extra Poisson part, so it's the coefficient of variation of the gamma. The gamma has variance v and mean mu when it has a coefficient of variation of sigma over mu, and this squared is what we have here as alpha. So, what I now want to do is, let me switch over to my R for that. I want to simply quickly fit this GP distribution, and what I now do is, I said before, we have replaced the log normal by the gamma. Simply because this is what when you can solve the equation. Of course, this only works if the log normal and the gamma have sufficiently similar shape that it doesn't really matter. And if you look at this picture here of the gamma distribution, of course, as always, for sufficiently high parameter, it becomes a normal, and the log normal also becomes a normal if the variance is small enough. But even for about the lower things like this thing, this actually has the typical skew that you also see in a log normal. So gamma and the log normal are pretty similar, unless as long as you stay in the parameter regime where you actually have a mode here. If you're in this parameter regime where it's simply monotonically falling, then of course it doesn't look like a log normal. But just to convince us that this actually works, I will now do a thing that I will simulate drawing from a log normal Poisson, and then we'll try to fit a gamma Poisson and see if I still get the correct parameters. So I simulate with eta now 1000 values from a log normal with mean 2.5 and standard deviation 3. Obviously I have to exponentiate it because it's log normal, and I use this as right parameter for my Poissons. And now I get this Poisson distribution here, where you can see how often I got each values in the range of the 36. And now I want to find the best fitting gamma Poisson distribution via maximum likelihood. And I do this as follows. dn by norm is the distribution, the probability mass function of a negative binomial. So this thing here. This thing is implemented in R as dn by norm. And in order to get it, what you're supposed to give R is two parameters, mu and size. Mu is the mean, and size is with 1 over alpha. So size is with R here. And I tell D and B norm that I wanted to report the logarithm, because in maximum likelihood we have to, of course, get the joint probability of all these observations. If we would multiply all these probabilities, we get an incredibly small number. This is why you do maximum likelihood optimization always with the log scale, and you tell the distribution function beforehand, so that R doesn't even try to calculate these gamma functions and then take the log, but rather it calculates right from the beginning the log gamma function, which has its own series expansion and hence has an efficient way to calculate it. So, doing this, I have to, of course, give my optimization a starting value. I say mu is 10 and size is 0.1, and then you see that after 67 function evaluation using some Newton-Raphson type optimization, it has found the optimal value for this likelihood sum. It was looking for a minimum, but I want a maximum. That's why there's a minus here. And it told me this maximum has here a mu of 12 and a size of 12. Now we can ask, is this what we expect? Is 12.6 the value that we expect? Of course, it is the mean of our K. But it's also what we expect from our original distribution, because we said we take a log normal with mean 2.5 and standard deviation 3. So if I want to see what this is, I have to take x 2.5, and as I told you before, because of the skewness, I also have to write it like this to get 12.74. So this is the mean that we specified, and 12.62 is what we got back. So this works. The other thing we have to check is the size correct. As I said, the size is 1 over alpha, 1 over 12.35. And alpha, as I told you, is the square root of the coefficient of variation of the underlying gamma. So this of the underlying gamma, or in that case the underlying log normal. So I can take the mean of this thing, divide it by its standard deviation. And actually, this coefficient of variation of a log normal is the standard deviation of the underlying normal, so it is 0.3, and that's what we get back here. So You see 0.3 squared is of course 0.09, and alpha is in fact nearly 0.09. When you work with this, it's always a bit important to keep all this reparametrization in mind, that alpha is the standard, is the variance of the underlying log normal, or the log of the logarithm of the underlying gamma, and that it turns up as v mu plus alpha mu squared in the variance of the final. Of course, I could have gotten the whole thing much easier by using method of moments. I told you that the variance is mean plus alpha mean squared, so I can simply estimate variance and mean from the data, variance k, mean k, and solve this thing for alpha and say what is the variance minus the mean is divided by mean squared, and then I get again my point nothing. If you do this with data with only a few values, like in our typical RNA-seq where we might compare 5 samples, this often doesn't work, because for this to work, of course, the variance has to be larger than the mean. But in expectation, the variance cannot be smaller than the mean, but in specific realizations, it can. And that's an issue why you typically don't use the method of moments, but the maximum likelihood. Here I used my optimization simply with this general purpose optimizer of R, which simply takes a function and then tries around the parameters, trying to do some, binary search for a root or for a minimum. And but if you want to do this a bit more clever, you can have an optimizer which is specifically written to work with this gamma Poisson, with a specific density of a gamma Poisson. And actually, Konstantin Allmann-Elze, who was a PhD student at EMBL, currently is hanging around in our group until, so Konstantin wrote this GLM-GP function as part of his thesis, which now everybody uses because it works better than the thing which is part into R. And you see you can use it for the same thing. I simply tell it, here is my count K, and if you then run it, it will give you mean and the value for alpha exactly the same as what we try per hand optimization. But the normal optimization tends to often not converge properly, and this thing always does. It also has a couple of important extra things. One thing is called Cox-Wright adjustment. You might remember from statistics that there's this thing called Bessus correction, that if you calculate the variance of a normal distributed data, the variance that you calculate from a maximum likelihood estimate will always overestimate the variance, and you have to subtract something to account for the fact that the true variance is a bit higher than the apparent variance because your sample mean is not on the actual mean. And this is called Bessus correction. And when you go to other distributions, like our gamma Poisson, you have the same issue, namely the gamma Poisson has this effect that the alpha has the role that the standard deviation has in a normal distribution. And we again have to make an estimation, and the Cox-Wright adjustment is sort of the equivalent to Bessus correction for or the generalization of it to the case of this distribution. I'll explain the over-dispersion shrinkage later. And if I switch on this Cox-Wright adjustment, then you will already see that my estimate for alpha goes up a bit because it was too low. It should be 0.09, but it's only 0.08, but it doesn't make much of a difference. So, next thing, GLMs. Let's go back to our original case, to the data we had before with exactly the same code as above. We get these counts K here by simply getting for each of our groups A and B counts with the specified true means. And now I want to, instead of doing a t-test, I want to fit a gamma Poisson model to this with maximum likelihood. And I fit it by saying the counts come out of a gamma Poisson with a fixed alpha, which is the same for all of them, and a mu, which depends on the group. And I write the mu as follows. My mu is some beta naught, which is the mean for group A, plus beta 1, which is the difference between group A and B. And in order to include it only when I need it, I introduce this indicator variable xi, which tells me whether sample I is group A when it's 0, or whether sample I is group B when this xi is 1. And of course, I have to multiply by the totals, S, the total read count, and before I always sort of meshed this in here in front of the mu. Now I pushed it here through the log and put it here. And now, of course, I can tell my maximum likelihood fitter that it should fit that, and if I call this GLMGP with this model formula till the group, it will understand from that it's supposed to fit. Hey, what have I done here? It's supposed to fit a different mean depending whether it's out group or with group. So what it actually does, it uses a model matrix tilde group. So whenever you tell R such a formula, then R internally calls this model matrix function, which then gives us two columns of coefficients for this logarithm here. The first coefficient is always included, that's why I get a column of ones, and the second is only included for the second 5 samples, that's why I get 0 here and 1 here. So this column here is this x1 here, and the first column is the 1 which is sort of hidden here. What's missing here, log Si, is the so-called offsets. An offset in a linear model is a term which is included in the model formula even though there's no coefficient that needs to be fit. And I should have added this here, and now I noticed I haven't. So let me add here, comma, offset equals log S. Is non-zero and additional size factor is fast. Okay. I should probably it has some clever function to automatically estimate the offsets itself, but I want to switch it off and just use the S as offset before. And if I now do this, I now get here my beta values, and I get my over dispersion value. And here this offset, here this factor for group B is of course exactly the logarithm of, should be the logarithm. What went wrong now? I put an S here, maybe I should have made, it worked without the offset before, now it doesn't work anymore. Okay, I probably should have checked this beforehand, because now the betas give us what we want here, with the proper fraction, etc. But independent of the fact that I've done it wrong, you can see what we have to do, what we do here. Our GP thing fits this model by finding factors for the beta naught and beta 1 by maximum likelihood fitting. What it actually does internally is an algorithm called iterated reweighted least square, where instead of just finding by brute force optimization the betas which maximize the likelihood, you linearize this log and go through and transform it into an ordinary least square model, into a weighted ordinary least square, which is sort of a linearization around your current estimate, and you iterate this, and you can prove that this procedure gives you the same effect as the normal optimization, but it has but it converges much faster. And so, and what I now want to do here, what I can now do, of course, is I can ask, does this plotting thing that we do here? Here I put in the size factors. What I can now ask, is our GP really better than the Poisson case? when the simple t-test that we did before. And I try this here by using my code where I simulate data and I let this run 300 times, and each time I run a t-test and I run the GLM-GP, and then I get out here the p-values which I get from either the two. And as you can see, the p-value of that I get from the GLM can get much lower than the p-value that I get from the t-test, which means that the GLM has higher statistical power than the t-test. Now, obviously, whenever we notice that a test has higher statistical power, the question which we should ask, is the test maybe cheating? Does the test maybe have a tendency to give me a significant result, even though I don't get even though the null hypothesis was true? In statistical jargon, the question is, does the test hold its size? So let's ask whether this test holds its size, as they say so nicely, by simulating, running the same code as before, but this time I put the expected mean for group A and B to exactly the same value, so that there's no difference. And now I ask, are the p-values now uniformly distributed? Because if the null hypothesis is true, then p-values should be drawn from a uniform, from a standard uniform. And I now ask whether these 300 values are drawn from a standard uniform. Now there's a little trick when you do that. Typically, if you have some data and you want to ask, is it drawn from a uniform, then the usual thing would be to make a histogram and just ask whether this histogram is flat. For p-values, this is not a good idea, because in a p-value, imagine the p-values are sort of uniform, except in the leftmost bin of my histogram. I have a tendency of seeing many more values like 10 to the minus 3 or 10 to the minus 4 than I would expect under a uniform. This doesn't help me much, because I don't see this in a histogram, because all the deviation or the evidence that the test doesn't hold its size is hidden in the leftmost bin of my histogram. Hence, when checking the size of a test, you never do histograms. Instead, you do what's called a QQ plot. For a QQ plot, I take all these values here, and I sort them, and then I take an equal number of evenly spaced numbers to mimic the uniform. So if I have 300 values, then I just take 300 equally spaced values from 0 to 1, excluding 0 and 1 itself, because I don't want to hit the extremes. So I go from 1/600 to 599/600, always going up a step 1/300. And I plot this on the other side. In order to see deviations on the log scale nicely, I plot the logarithm of these. And here you can see how this works. If they are truly uniform, then the occurrences of really small values should be no more often than in our actually observed supposedly uniform data than in our idealized uniform data, where I just take the 300 theoretical quantiles of my data, because that's what it actually means to take these 300 values equally spaced from 0 to 1, including the extrema. That means that I have split the quantiles of my expected distribution in 301 pieces and take the breakpoints of these quantiles, with each piece having the same probability. And if I compare these two, then you can see now how this looks like. For this one here, for the t-test here, it looks perfectly fine. They all sit on top of this line. It seems that, of course, the smallest p-value I see just in the sorted thing is this one here, 1/300th, and here we see about the same, and I put this diagonal line to show this. This is called a quantile plot, because we compare the actual quantiles of our empirical distribution with the quantiles of the theoretical distribution. And for the GLM, last time I ran it, it was also sitting on the line. When I reran the thing to upload it onto the web page, and with the new random numbers next time, it didn't hold its size. Bad luck. I wanted to say, look, it works. But in general, there is a reason why these generalized linear models often don't hold sight properly, and that is because, wait, I haven't told you yet how the p-values actually get calculated. So what you do to calculate the p-values in such a thing is we have maximized the likelihood. Now you consider the likelihood here is a function of beta naught, beta 1, and alpha, because these are our three parameters to parameterize our distribution. Now we fix beta naught and alpha to their optimal values and consider it only as a function of beta 1. That's called a profile likelihood. Profile likelihood means restricting a likelihood to only one argument by keeping the others to their maximum likelihood estimate. And I can calculate and I can look at that thing. And of course, typically, it should be close to the maximum. It can typically be expected to be parabolic. Ideally, if the likelihood in question is a normal distribution, it's exactly parabolic. Otherwise, it's usually approximately parabolic. In other words, we ask what is the second order Taylor expansion of our distribution at that point. And you can show that this, and in a normal distribution, this second order Taylor distribution of the log likelihood is, of course, let's write this down. If your normal is 1 over 2 pi sigma e to the minus x minus mu squared over sigma squared. If I take the log likelihood of this, add it up over many samples, then what I get is sum over all my samples minus xi minus mu squared over sigma squared. And you can imagine if I then consider this as a function of mu and sigma, and I fix sigma to its optimal value and ask what is the second derivative of this likelihood with respect to mu, then the coefficient will of course be 1 over sigma squared. And hence, with this, of course, you can write a whole dissertation in theoretical arguments why this is proper even for non-distribution, to which extent it works. You say that here the Taylor expansion is exact after second order. And if I want to know how precise my estimate for mu is, I know, of course, that the precision of this estimate, usually the variance of an estimate for mu is, as you know, sigma over square root of n. So if I take my second derivative, take the square root of the reciprocal square root of it, divide this by the square root of a number of values, this would give me the precision of the mu estimate. And that is generally taken over. So whenever you have a parameter theta, and so you have your log likelihood, let's call it. So you have your log likelihood, log of some distribution function of a couple of values theta. So theta 1, given some data, and you ask what is the derivative with respect, and you take the derivative with respect to this thing, given that theta 2 from theta n is the specific optimum, then you get a certain value which, what do I call this value? Well, let's take this thing, say we take this to the minus 1/2 and say this will typically be a reasonable estimation for the variance of the estimate of this theta 1. So the whole theta is at the optimum, not only this, after you divide by the number of degrees of freedoms, etc. I hope I read that correctly now. So this is in general what you do. This is called a Wald standard error that you get from this. I don't know whether Wald was German or American. I think he's American, otherwise I should call him White and remember where he was from. And yeah, this is what you usually do to estimate these standard errors. If you do this with a normal distributed thing, what you get is when you have one extra thing, because we take the sigma as known. And as we just mentioned before, actually, when we use the we have two issues. First, we need to adjust the sigma. That's what we get with our Cox-Wright adjustment. But more important, we also need to take into account that the sigma is not optimal. That, of course, the place where we estimate this derivative depends on the value of the others, which themselves have an error, and they influence each other. And in case of a normal distribution, you account for this by making an F-test. So you assume, by assuming that this thing follows a T distribution rather than a simple normal distribution. And we need an equivalent for this in our, here in our GLM framework. So in the normal linear model ANOVA framework, what you do is you compare the estimate and its standard error with the T distribution. So what you say is that this, I don't try to write it now properly, I just explain it worse. What you usually do, you have your estimate for the coefficient, for the beta, or for the difference in mean, or whatever this is. You divide it by its standard error and say, once you have divided it by the standard error, it should follow a normal distribution with standard deviation 1. But because the standard error might have uncertainty associated with it, the actual distribution is wider, namely the normal distribution gets widened to a T distribution. Here, the question is, the T distribution shape comes specifically out of the specifics of the normal distribution. Can we really generalize the mathematics and also use the T distribution here in order to get our to get a p-value out of a standard error? And there's some debate about it. In the software, some software simply says, now we don't really know how many degrees of freedom we have, hence we don't know how much wider the T distribution should be, so let's better take the normal, which of course is an anti-conservative thing, because the normal of all the possible distributions is the smallest, so the one which gives the smallest p-value. This is, I'm now not quite sure what the GLM-GP function exactly does. There's different choices what people do, but the traditional thing that most software packages do is to calculate the p-value, assuming that that all the other parameters are exact, which underestimates the p-value, which gives you too low p-values, unless you have more than 20, 30, 40 samples, when the uncertainty of the variance parameters is so small that it doesn't really matter. As I said, it depends on the details of the implementation, whether it does this or not. But this is one of the things you always have to look into and account for. And there was further. I'm sorry, I have a feeling I keep forgetting what I wanted to say today, so I won't get more into these details. But yep. Instead, let me quickly look at what we have in how this now looks in practice. What I told you before, is I took this. Where am I? I now want to apply this thing on our actual data, So what I've done is I again load the same example data as last time with IFND. Then I found here this other table, which actually I found somewhere else, which tells us for each cell which donor it was taken from here, which individual, some strange individual numbers. And I add this to our data set. And now I calculate it with pseudobikes by going through all the cells, and for each cell I ask, get me all the cells from this donor, which are controlled, put them, add up all the columns, all these columns, and then into one big column, and then in this way I get here my byte count matrix. What I also need is a sample table, which now tells me for each column of my count matrix what data this is. And as you can see here, I get the samples, the donors, and the condition. And from this and this, I can now go to this GLMGP here. And if I run it, I should get in a second, I should get a result. Shell. I think it took 20 seconds last time. So, and as you can see here, what it now gives us, it gives us lots of, for each gene, it gives us the coefficients. To understand the coefficients, we should have a look at the design matrix, which is implicitly put here. I put this here, and here, and here. Now you can see how this design matrix looks like. It looks slightly different. I don't have my columns of ones here. Instead, I have for each donor an intercept column which has a 1 in the samples from the respective donors. That's why this is going down. And then I have my condition column, which is 1 if it's stimulated and 0 if it's unstimulated. And these are the coefficients in front of the betas, and the betas are, these ones here are then the corresponding values which we estimate. So these are the sort of the expression strength of the gene in the donor's unstimulated sample, and this is the average increase from stimulated to unstimulated. And then I can again do this DE test, which I really should have looked up exactly again to see how it calculates its p-value, whether it's a word test or the other thing. And now I can make an MA plot, and in this MA plot, here I plot on the x-axis the average expression, on the y-axis the log fold change, and I would make them red if the p-value was small. You see, this thing looks ugly, and it's in a way an artifact from all the zeros, because whenever I see a 0, then of course the associated beta value would be minus infinity, and it somehow clamps it down there. So what I now do, I zoom in and only show you this thing here, which is the actually interesting part. And yeah. Yes, exactly, it's the same plot. Nearly the same plot, except for some differences. And here you can now see the genes which go up on top or down at the bottom. And I have to quickly explain how we make them red, because you see I took this not from the p-values, but from the adjusted p-values. That's the Beniamini-Hochberg adjustment. Anybody has heard of that one? So whenever you do these kinds of differential expression testings on a big chunk and lots of genes, you have the following issue. Imagine we decide to make all those genes red which have a p-value below 0.05. Then even if there were no difference whatsoever, if the stimulation would just have been water, we would still expect 5% of the genes to be red. Because even under the null hypothesis, 5% of the p-values will be below 5%. So if we now notice that we actually, if we now decide to cut at 5%, and we notice that actually 10% of our points are now red, and we conclude 5% are just will always be there, and 5% are probably the real thing, hence half of them are fake. And we call Beniamini and Hochberg suggested to call this the false discovery rate, and say and it's defined as follows: you choose a threshold where you cut your p-values into significant and not significant. When you ask which percentage of all my genes are actually below the threshold, and you divide the threshold by the actual fraction, because the threshold is the fraction we should expect. So let's say we decide on a threshold 0.02, when we should expect 2% to be deemed significant even under the null hypothesis. And if I divide this 2% by the fraction which are actually found to be below 2%, I get the fraction of null results or of false discoveries among my list of red genes. And what I can now do next is I adjust my threshold to find a suitable target place. And here I've adjusted the threshold and said choose a threshold such that the false discovery rate is 10%. And in order to do this practically, what you can do is you just do this calculation for each individual p-value. For example, I asked which percentage of the genes have a p-value below 0.202. I say, okay, this is a fraction of x. I divide it 0.202 divided by x, and I get this number. And I can interpret this number as saying, if I were to cut my list into significant and not significant and put the cut point exactly here, then this would be the false discovery rate. And hence, I just say I want a false discovery rate of 10%, so I keep all the genes where this value is below 10%. And the nice thing is, if you think about it a bit, you will realize that in order to calculate this column, I don't have to do this logic that I've just said of counting how many are below that for each gene separately. All I have to do is to sort this column by p-value, and then I can go down through the list and always say, okay, I get now one more real gene, and this thing goes up, and in that way you can just write down this list by going through this list in a sorted fashion. And all you need to know is the rank of this thing, like this position in the sorted list, to calculate that part here as a simple fraction of rank divided by the value you see here divided by the rank multiplied by the total number gives the adjusted p-value. That was this neat little trick that Beniamini and Hochberg found, which is always called the Beniamini-Hochberg adjustment. Of course, the neat little trick is the more obvious part. The less obvious part was this idea that the false discovery rate isn't useful, because before, in statistics, people always talked about something called the multiple hypothesis burden. They said, whenever you do a statistical analysis where you test many different hypotheses, you have to account for this by making sure that you replace your p-value threshold by something more stringent than usable. So if instead of testing one hypothesis, you test 20 different hypotheses, when one Ferroni suggested you should replace the usual 5% threshold by 5% divided by 20. If you use this logic for our 20,000 genes, you won't find anything. And that's something that upset people a lot. And then Benjamin Hochberg came along and pointed out that actually Bonferroni's argument is correct, but what Bonferroni's argument controls is what's called the family-wise error rate. It tries to control the probability of there being a false discovery among any of the hypotheses. And this makes a lot of sense if you're in this situation here, which is always, I hope you all know XKCD. Where is XKCD? Why did I overlook it? Here it is. So, you see the usual thing. Somebody makes some strange claim. You do a test. You compare the amount of the occurrence of acne between people who eat jelly beans and who don't. Find a p-value larger than 0.05, which, according to standard medical literature logic, or maybe old-fashioned sees that it's not significant. Of course, it's already wrong up to here. You would have to do a power analysis and find out whether your sample size was big enough to actually get a low p-value in case it's true. But let's assume they have done that correctly. Then it might still be that you have to substratify and say it's only a certain color. And then this will go happen. We found no evidence in purple. Next team says no evidence for brown, no evidence for pink champions, except for these people here. Because obviously there's 20 different colors, so it's quite likely that one of them gets a p-value below 0.05, and then you get this, which is of course a thing which probably played out actual science or in bad science reporting more than once. And Bonferroni says, well, of course, to get 95% confidence, they should have compared not with 0.05, but with 0.05 divided by 20. And here Bonferroni would be perfectly right, because making only one mistake already ends in the disaster of having a completely misleading headline. But in our case, it's different, because, as I said in the beginning, we already know that there should be differential expression, and that probably all genes are expected. We only don't know the correct direction and so on. So if we keep this in mind, then we can use Benjamin Hochberg's logic. So Benjamin Hochberg's point was, you have to distinguish between statistical analyses where making a single mistake already causes a dramatically wrong conclusion, like this one, or where a single mistake is not so bad because we already know that there should be some genes, we just get a list, and if we say we know that some of the lists will be wrong, then it might be sufficient to not control the probability of making some error somewhere, of just trying to get an estimate about how much wrong results are in there. And once you switch your frame of mind to this other goal, you are able to actually work even though you have 20,000 hypotheses to test for 20,000 genes, which would completely kill you in the Bonferroni case. So, and that's why we have to do this beforehand, before we choose here where we go with these red genes. Another thing which we still need to keep in contrast is the strength of change. I told you the red only tells us that we got the gene wrong, right? And as you can see, the weakly expressed genes tend to have stronger fold changes than strongly expressed genes. But of course, we know that this is just due to variation, because the Poisson noise is stronger for the weak genes than for the strong genes. So the variance, the standard error of the log fold change is stronger here. Now, in principle, our testing procedure should take this into account, and that's why we need stronger evidence of a difference in order to believe it for the weak genes. But still, we have a confirmation bias issue here. Those genes which pass the thresholds are more likely to have a log ratio estimate which has a large magnitude. Overall, we know that the expectation of a log ratio estimate is 0 if we normalize properly and if there's equally many going up and down. So the individual log ratio estimate by itself is unbiased. But the log ratio estimates for those genes which have been deemed significant, they all have an upwards bias, because a gene which is deemed significant is more likely to have a variance which is too high in magnitude than which is to have a fold change which is estimated too high in magnitude than too low. So all these values are likely to overestimate, at least the red ones, while the black ones maybe were even underestimated. And that makes it difficult if I now want to pick the genes which have the strongest difference. I want to know which genes might be the most interesting, that one or that one. And I want to get to the question of what might be proper way. And this is where we do shrinkage estimation. We try to replace our log ratio estimates by estimates which are deliberately shrunken towards the 0 line. and that's called in statistics a variance bias trade-off, because as I told you before, in principle all these log ratio estimates should be unbiased. But here to the left they have increased higher variance than to the right. If I now try to compensate by pushing them towards zero, and the higher the variance, the more I push them towards zero, I reduce the variance and I buy this by increasing by introducing a bias. And that's often quite useful to make this trade-off of saying I introduce a bias, I accept the bias to reduce variance, because the individual estimate will then be closer to the real value, will then be more likely close to the real value than before. Which, you see Andreas looking very surprised. When James and Stein were the first to point this fact out, it caused about 20 years of head scratching in statistics. It runs under the term James-Stein paradox, who said that well, you can look at it yourself, who said that it can be that you do a transformation which makes every individual estimate worse, but still improves the overall performance of the estimator over all the different observations. And that's something we use a lot here in order to make our stuff comparable. Now, there's a lot more to be said, especially how to do this variance bias trade-off best, how to do this with empirical Bayesian bias and so on. But even for this is something I like to talk about, because I've worked on this topic in my MBL time. I think I stop here, not only because it's 5:30, but also because we will switch topic and then come to denoising by autoencoder hopefully the next time, and you will see that one of the reasons I introduced this is because we will need the gamma-Poisson distribution, because we will have to think closely about how to properly estimate, quantify reconstruction accuracy, which when we talk about PCA, we simply did by saying we want to minimize mean squared error. We will realize that this is actually not good enough to get good results, and that instead we have to use this gamma-Poisson likelihood. So, that was it for today, except for one thing that I wanted to mention. I told you last time I made you this little homework problem. As I said, my idea would be I would like that everybody, or at least everybody who wants to get it right, have at least one little thing. I was a bit awake, being myself a bit confused about how much I actually want to do, but now I thought I'd probably do it. One of you already sent me a little something to diffusion distances, which was fine and nice, but those who haven't looked at anything yet, I will now start whenever I have a good idea to add a bit of these homework things. Here I've added now 2 homework problems that would be sort of typical things, and I think both of them I sort of, you see, I started with something simple, and actually I wrote a lot of math, but actually you probably don't need this, and then I started switching to a bonus task and thought, okay, if you just want to prove that you are able to do a bit of programming, do it up to here, and if you then get into it and want to start getting interested in the topic, then here's a lot of other stuff you can also try out. Yeah. And I'll probably see what else I can add to that. Yep. So that's what we have for today. Then see you on Wednesday or next Monday. Probably on Wednesday. Let's see what we do there. Maybe already try to get the autoencoder working. Then those who